Welcome to the talk, Easy, Adaptable and High-Quality Modeling with Domain-Specific Constraint Patterns. My name is Dr. Sophia Saller, and today I will be talking about joint work with Professor Dr. Jana Koehler. Let us start by talking about patterns in general. Originally, patterns were introduced in the domain of building architecture to describe best practice or expert solutions to recurring problems. A pattern describes such a recurring problem, gives a solution approach to this problem, and highlights consequences of choosing this approach. Several years after the introduction of patterns in the domain of building architecture, the idea of applying design patterns was extended to the world of programming for designing reusable solutions to common software engineering problems by the so-called Gang of Four, Erich Gamma et al. But such recurring problems do not just occur in building architecture or software engineering, but also in constraint programming. This led us to thinking about how patterns can be made useful in the constraint programming setting. Constraint patterns, as design patterns for constraint programming, were first introduced by Toby Walsh to help constraint programmers spot commonly occurring anti-patterns, which make models inefficient and describe expert knowledge on how to best resolve these issues. However, these patterns are not domain-specific and instead general modeling techniques. By making constraint patterns domain-specific, we allow for the inclusion of problem-specific modeling ideas and explicit implementations, which can further improve the quality of the final model. Before we look in more detail at what we mean exactly by a domain-specific constraint pattern and how these should be described, let us first discuss their advantages. Firstly, easy modeling. We aim to reach a stage where, for common problems, the modeling process consists of a human modeler simply picking the applicable patterns from a large library of patterns and combining them in a model. This has the potential to vastly simplify the modeling process. Adaptable modeling. In real-world problems, the problem we wish to model may frequently change to some small extent. Since the constraints are directly related to the patterns, we can easily swap the constraints relating to one pattern for those of another if the situation changes. High-quality modeling. As I'm sure we are all aware, for a constraint model to be useful in practice, the model needs to not only be correct, but also be of high quality to help the solver find solutions fast. Domain-specific constraint patterns make expert knowledge on how to model problems in order to simplify the solution-finding process for the solver more easily obtainable for others, which will result in high-quality modeling. And finally, explainable modeling. Domain experts have an in-depth understanding of the problem at hand, but in most cases, they do not know how best to describe these constraints mathematically. Domain-specific constraint patterns contain explanations of the intent of the pattern in plain English. This allows for constraint modelers and domain experts to lead discussions at the abstraction level of patterns, which can be easily understood by both, rather than having to lead the discussions at the abstraction levels of constraints. In the paper relating to this talk, we introduced domain-specific constraint patterns on the example of production scheduling problems due to their practical relevance. For these type of problems, a classification schema exists, consisting of alpha, the machine environment, which contains just one entry, beta, the processing characteristics, which may contain multiple entries, and gamma, the optimization objective. The idea here is to introduce a pattern for each machine environment and each processing characteristic, where the pattern for the machine environment determines the variables used in the modeling and includes some constraints. The implementation of the patterns relating to processing characteristics may then depend on the modeling of the machine environment used in the problem and consists of constraints, but also potentially further variables. We are planning to extend the pattern repository to further problem classes in due course. One of these are traveling salesman problems and their variants. For these, we are currently working on a similar classification schema for TSB problems. Let us now look at the description of domain-specific constraint patterns. We base this description on the well-established pattern template by Gamma et al., which we have adapted to the constraint programming setting. Firstly, the intent explains what the constraint pattern does. The motivation explains the motivation behind the pattern. The applicability entry gives conditions on the situations in which the pattern can be applied. We will look at the applicability entry in more detail later on. The diagram entry shows a diagram displaying the pattern. The participants entry lists the variables participating in the pattern. The collaborations entry explains how these participants collaborate in the pattern. The consequences entry lists any consequences of applying this pattern. The modeling variance entry gives variants of the best practice modeling of the pattern for different modeling languages. The forces, enables, compatible with, incompatible with entries give relationships to other patterns. And finally, the search strategies entry lists search strategies that are known to work well in the setting of this pattern. Here you see an example of a pattern description for the job shop pattern. In a job shop, jobs consisting of operations are processed on machines. For each job, the route through the machines is predetermined and fixed for each job, and each machine can only ever process one job at a time. Due to the time limitations of this talk, I will not go into more detail here and direct you to the paper or the website for more information. Let us instead look at an example of how we can apply domain-specific constraint patterns. Suppose we are given the following scenario. A set of products are to be processed in a flowshop environment. Further, a set of workers exist, where one worker needs to be present for the processing of each operation. Further, as the machines are some distance apart, each worker takes a certain amount of time to walk from one machine to the other. In terms of pattern, we can describe this problem using just three patterns: the flowshop pattern, the distinguishable resources pattern, where the resources are the workers, and the resource setup times pattern, where the setup times correspond to the walking times. To assemble a constraint model using the patterns, for example in IBM Cplex, we simply take the modeling of the variables from each constraint pattern, combine them in a model, then add the objective, and finally add the constraints relating to each pattern. And we have obtained a constraint model for the problem scenario. Clearly, this relies on all constraints we may have in the problem to be part of constraint patterns. But even if they are not, the pattern model gives the basic structure of the constraint model to which more constraints can easily be added. In the applicability entry of the pattern, we give conditions which must be satisfied by a corresponding event log for the pattern to hold. You see an example of a small event log at the bottom of this slide, so you can get an idea of what we mean by an event log. These conditions can be automatically checked and do not make any requirements on the quality of the schedule in the event log. For example, if a company has thus far relied on humans to make schedules for their production, they can simply check whether certain patterns occur in the past event logs, and from this, assemble a constraint model for their problem. By stating the conditions separately from the constraints, we can also allow for small margins of error in the conditions, for example, to allow for noise in sensor data. Using this, we can achieve what we call CP DevOps, the DevOps for constraint programming, which you can see on the right-hand side of this slide. We start with an event log, on which we can automatically detect which patterns occur in the problem. This is step A. Once we have the set of patterns that occur in the problem, a human modeler can assemble a parameterized constraint model from the patterns by using the explicit implementations of the patterns. This is step B. With the model, we can find solutions to future instances of the problem by using a constraint solver. This is step C. And finally, by executing a solution schedule, we again obtain an event log, which is step D, on which we can again check the patterns to detect any problem drift. A more detailed discussion of the applicability entry and CP DevOps can be found in the paper. This leads me to conclude this presentation. We have introduced the idea of a repository of domain-specific constraint patterns, which can automatically be checked on event logs of processes. These patterns can easily be assembled to constraint models by either using human expertise or for specific problem classes automatically to obtain high-quality models. And finally, an online pattern repository has been set up under www.constraintpatterns.com and is currently being populated, and already contains several production scheduling patterns. We would love to hear feedback about it and are welcoming contributions, comments, and suggestions for improvements. We are further currently working on an automatic pattern checking tool. This brings me to the end of my presentation, and all that is left to do is to thank you for your attention and reiterate that we would love to hear from you.